What's up, guys? So I have an anatomy quiz this morning, and I just wanted to show you guys a bit of how I study for that. So my quiz today is going to be on the urinary system, and I got some time to go through some of what I'm studying, and I'll show you guys a bit of my study methods. So, of course, as we did last week for our last quiz, results from the last quiz that turned out to be, I got an A on that quiz and had some extra credit too, so that was pretty awesome. Okay, so I'm going to show you guys some of the recent notes I've taken. I'm going to be going over today. It's always a good idea when you're taking anatomy to go over your notes, especially if your teacher's really very much in depth on the topic. It's important to star some important questions that your professor might ask the class, or some more of the notes, important figures from the book to cite, missing information. It's important to keep all tabs on these types of things. Okay, so I'm going to be jumping through a bit of that today, and I'll probably even show you guys some of the pictures that I'm reading in the book. Also, it's good to highlight some stuff in your anatomy book. It helps you understand urinary system much better, because when you talk about things like the kidneys and hormones and things like that, it's very much needs a bit of a visual appeal. Okay, similar to last time, I'm going to start with the 6 main functions of the urinary system. Most are done by the kidneys, of course. First we have ions that are involved in the functions of urine. So there's atoms. Some of these atoms can form amines, and I'll show you guys a picture. So this is the figure I'm talking about right now. Kidney anatomy right here. So understanding your basic kidney anatomy is very important. So the atom I want to talk about is amine. So amine is made up of proteins. It has constituents, so nitrogen comes in the form of food. So when we eat food, we get nitrogen, and it gets broken apart into amines. So food goes in, we break it apart, we get amine. Okay, and it makes up a negative and positive charges on nitrogen. Okay, so the body needs to figure out what to do with that ammonia, excreting it through so amine is able to be become ammonia, so NH2 becoming NH3, and that's kind of dangerous because ammonia can be very toxic to the body. So the body needs to figure out what to do with that ammonia, so it decides to excrete it through boldness and as a non-toxic form. It's formed in the liver and is excreted in the urine. So the ammonia is formed in the liver, excreted out in the kidneys. Just going to grab something real quick. Sorry about that. Okay. So the liver detoxifies ammonia by putting it in the form of urea. So ammonia is controlled, so it's no longer toxic because it becomes urea. Here's a picture of the structure for that. Right there. So this structure has an amine group, NH2s, and an acid group. NH2 can act as a buffer, taking on a hydrogen ion and becoming NH3, ammonia. Ammonia is bad because it kills cells, so it's toxic. To stop ammonia from killing cells in the liver, the ammonia is combined with carbon dioxide. So ammonia plus carbon dioxide forms urea. And where do we get the carbon dioxide that's combined with ammonia? The carbon dioxide comes from cellular respiration. So things like your glycolysis and the citric acid cycle. So my professor asked the question, why do we always have a ready supply of carbon dioxide all the time? It's because of cellular respiration, as I said. What is one number one issue for kidneys? Getting rid of nitrogen waste and waste from amine groups becoming ammonia. So that's an issue for kidneys. Getting rid of those things. Okay, amine groups becoming ammonia. Cellular respiration. So cells are taking in oxygen, doing their metabolic thing. They're spitting out carbon dioxide as a waste product. There's no shortage of carbon dioxide at this point. Like the liver wants carbon dioxide, and you end up with urea. So liver wants carbon dioxide, so it's able to combine with that ammonia to become urea. So urea, CH4N2O, has two amino groups, a carbon and an oxygen. Urea is a less toxic form of ammonia, is a form of ammonia combined with carbon dioxide. The kidney isn't used to metabolic processes. The kidney is used to grabbing a whole lot of blood and putting it back in. The result is excreted filtration system. Another function of the urinary system is to regulate ion concentration for a lot of ions in the blood. So regulating and controlling the levels based on current needs. There has to be a feedback loop. The kidney regulates ions in the blood, making the decision whether to conserve the ions in blood or excrete the ions by dumping it into the urine. So kidney is making decisions, store the ions or release it in urine. So the third function of the urinary system is acid-base regulation, deciding whether to keep hydrogen ions in the blood or does the kidney excrete it. Okay, like I said before, if the pH of the blood is high, very basic blood, then it should be the kidney will extract and excrete some more bicarbonate ions. So removing that base bicarbonate ions, so it's excreting that. The kidney will take out more bicarbonate from the blood and excrete it in the urine if the blood pH is becoming a little too low or acidic. So exercise forms carbon dioxide. Exercise creates acidic conditions. Carbon dioxide is produced every time we exercise or when the cells metabolize. H2O is also produced every time carbon dioxide is produced. It combines with water. Carbonic acid is transferred in the blood. Okay. How does blood pH in the kidney become too low or acidic? It's because of exercising. Increasing exercise or cell metabolism means we're producing more carbon dioxide, producing acidic conditions, and the body uses buffering mechanisms such as breathing. Okay, now we're looking at a different figure now, guys, so I'll show you guys that now. Now we're looking at this figure a bit more on the chemical side of things. Okay. My nose is very runny today. The kidney can't excrete carbon dioxide, but it can excrete more hydrogen ions if it were following it in the blood. Okay. Okay, tying up hydrogen ions by binding to them to hemoglobin. Deacidifying, taking hydrogens out of the blood, and acidifying urine. Dang, why is my nose so itchy? Sorry about this, guys. My nose is very itchy today. The kidney is removing hydrogen ions and making it less acidic, stopping formation of carbonic acid, same as the chloride shift, switching chloride with bicarbonate ions, deacidifying blood, sending them into the urine. Seriously, what the? The kidney is a buffer system for blood pH, regulating blood volume and blood pressure. So if you have increasing blood volume and increasing blood pressure, then you have Then if you have decreasing blood volume, you have decreasing blood pressure. How does the kidney do this? It makes decisions on whether to leave more water in the blood, raising blood pressure, or take more water out of blood. Okay, I gotta... Oh, dang. Okay, let's do this. I have a quiz soon, so I gotta keep this video going. Sorry, guys. Okay. So how is the kidney able to regulate blood volume and blood pressure? So, as I said before, increasing blood volume also increases blood pressure. Decreasing blood volume also decreases blood pressure. The kidney makes this decision of whether to leave more water in the blood, raising blood pressure, or take more water out of blood and send it into the urine. So if there's more water in the blood, there's more blood pressure, or if there's more water going out of the blood, that lowers the blood pressure. This is done with the help of endocrine hormones. Okay, we'll talk about those soon. So it's the same as the chloride shift, switching chloride with bicarbonate, deacidifying blood. The kidney is acting as a buffer system for blood and pH. So control of red blood cell production. The kidney isn't readily involved with this story, except for the fact that the kidney is the source of the hormone erythropoietin. Erythropoietin is a hormone produced by the kidney sent into the red bone marrow, where red blood cells are generated. Red blood cells. So, erythropoietin produced by the kidney and sent into the liver. No, sent into the red bone marrow for red blood cell production. For the liver is the one that gets the ammonia, and that combines the carbon dioxide in the liver to form urea. Okay, so the sixth function, the liver assists the kidney with detoxification of blood and with metabolic processes of blood doing chemical processes. Major structures or anatomy of the kidney. So there's two kidneys, two ureters, so those two beans, two ureters, lines going through the kidneys down to the urinary bladder, that's the muscle part, then to the urethra, and then out of the body. The kidney will then drag it out of blood and excrete it in the urine. This set of kidneys is in a retroperitoneal position with some important structures. The kidney has a fibrous capsule covering it, no viscera peritoneum because it's just behind the peritoneum. It has a parietal peritoneum on its face. It's shaped like a kidney bean. It has a dip in the center of the bean called renal hilus or hilum. So it's similar to a real bean, that dip. Renal sinus. Inside the hilus, there is a cavern in the back. The cavern is a sinus or hole. Sinus starts at a wide mouth called the renal pelvis, top of the ureter, branches into the smaller rows, 4 large highways, collection of small streams leading into a bigger river called calyces, singular calyx. So calyces, major and minor calyces are not obvious to see. Now I'm going to talk about renal medulla versus renal cortex. So we have renal pyramids. All the pyramids together constitute the medulla, or the cover of the kidney. The renal medulla is the core of the kidney. Core, not cover, core. Renal cortex is the outer region of the kidney, not within the pyramids. Renal columns are the dividing tissue between pyramids. Next figure. Okay, so this is the next figure we're looking at, more on the blood vessel system of the kidneys, or vascular system. Vascular system of the kidneys. So the figure that I just showed you guys shows how the vascular system does blood circulation, meets with tubing of the kidneys and arterioles. So it's a back and forth process between blood and the urinary system. It's fed by the blood. You don't need. My professor said you do not need to know all the vessels in between these two. So the major vessels to know are renal artery. Renal artery brings in blood. Brings in a lot of blood to the kidney. The renal vein takes in the oxygenated blood out. We have an afferent arteriole and an efferent arteriole. About 1,200 milliliters of blood flows into the kidney. There's a glomerulus. All these vessels ensure that the kidney has access to blood. So from renal artery leads into afferent arteriole. Afferent arteriole, think more towards, blood moving towards. And efferent arteriole, blood moving away until it reaches the capillaries, or renal vein, the capillaries. Okay, next figure. So this is the next one we're going to be talking about, some more on the nephron side of things. Nephron is the functional / working unit of the kidney. Lots of cells are working together, working on it. It involves pulling things out of blood and deciding whether to keep it or send it to the urine and send back into the blood. The kidney does a series of steps. So a series of events. First is filtration from blood to kidney tubules. Takes things out, filtration. And then reabsorption from the kidney tubules back into the blood, reabsorbing things from the blood, filtering things out of blood, then reabsorbing things into the blood. So reabsorption for kidney tubules back into the blood. Reabsorbing, so filtration. Blood to the kidney tubules. Reabsorption is from kidneys back into the blood. Secretion, secreting things out of the blood and back into the kidney tubule, so going back. Except it's moving substances out of the blood, filtering like a sieve at a beach. Only certain things can go through. Push on the blood because there is pressure on the blood. Happens, so there's pressure from behind. Physiological differences between the three processes of filtration is like a sieve. It will push that allows things that are a specific size through. No active transportation. It pushes like a proton in the happens due to pressure from behind. Filtration takes everything out of blood, where at the kidneys everything is screened and filtered to the point where only proteins small enough can fit through, like a sieve. Anything bigger will anything bigger will stay in blood, but smaller things will be filtered out. Glucose, amino acids are filtered out. Small things like these come out. Filtration happens at a little site called the glomerulus. So that's the only site on the nephron where filtration happens, at the glomerulus. Okay, so we have about 1 million nephrons. So if we have 1 million nephrons, it means we have about 1 million glomeruli working per kidney, so lots of working units. Yeah, because the nephron is the working unit of the kidney. So knowing the two kidney arterioles, efferent bringing blood into the glomerulus, efferent bringing blood away from the glomerulus. So knowing the filtering story, so there's no metabolism going on here. Okay, next figure. So onto the next figure is on the different types of nephrons. So there's a cortical nephron and a juxtamedullary nephron. Yeah, they're very similar, but you can tell that the cortical nephron is much smaller and juxtamedullary nephron is much bigger. And also they both have peritubular capillaries. You can see on the figure all the way in the left side, you can see that the cortical nephron is very much in the cortex. Juxtamedullary nephron is very much in the medulla already, so both will eventually lead to a papillary duct or renal papilla, and that's where urine is excreted. The glomerulus is a bundle of capillaries into which blood is being sent through the afferent arteriole and blood is leaving through the efferent arteriole. The glomerulus is connected to a whole series of tubes. Microscopic, it looks like a cross-section of tubing, giving blood access to your filtrate over a distance of tubing so that blood has a chance to remove and add things in. The 6 stages of exchange, so proximal convoluted tubule, exchange happens, or reabsorption happens at the proximal convoluted tubule, then to the nephron loop, descending limb, and ascending branch, where more exchange is going on. Distal convoluted tubule for more exchange also going on. Collecting duct collects what is left and can still do some exchange. Kidneys are in service to blood. Okay, so for the cortical nephron, once blood goes into the glomerulus, does its filtration and leaves glomerulus, it doesn't go out of the kidney. It then has the job of being passed around the tubing so that there is more opportunity to exchange. And it wraps around the loop of Henle, and it goes up and wraps around the distal convoluted tubule. The blood supply that is staying in close contact with the kidney apparatus. Okay. Okay, I gotta go through this faster. So 2 types of nephrons. Juxtamedullary nephron, the long loop, it's used to conserve water. So this one's close to medulla, or beside the medulla. Cortical nephron, shorter loop, 85% of nephrons look like cortical nephrons. Higher, animals have a lot of juxtamedullary nephrons because they have to conserve more water. The 3rd/4th function of the kidneys is regulating blood and water levels in the blood. Retaining water. Nephron loop is retaining water in the blood before urine leaves the body. Because it has some of its limbs permeable and impermeable to water and solutes. Okay. Conserving water in the blood and passing it back through the tubing. Vasa recta is not such a branching mesh of capillaries like the cortical nephron. Filtration process. Blood enters the glomerulus, through efferent and efferent arterioles. Each capillary is surrounded by a membrane, a filtration system, or a sieve. Membrane surrounds capillaries in cross-section. Capillary a little bigger than wall of red blood cells. Next figure. 26, I'll show you the renal corpuscle. So the glomerulus and its capsular space, basically. The renal corpuscle has capillaries that allow a red blood cell to fit through. There's jagged walls. Those jagged walls are, there's another figure for this. Here's the next figure, more on the walls type stuff. Okay, so the jagged walls have podocytes or foot cells with processes and pedicels. Pore/slits formed by endothelial cells limit what can fit through the capillaries. Ions, solutes, and water can go out metabolic ways. Products of cell responses, urea, uric acid, creatine, phosphate, sodium and nitrogen, proteins and triglycerides can't fit. Proteins and triglycerides cannot fit out. All under pressure, out comes ions. It's all under pressure, so push from behind allows more things to be filtered out because the urinary system can't make decisions of blood unless it has access to the blood. Out comes ions going into the glomerular capsules, proximal convolutes to the proximal convoluted tubule, and then to the distal convoluted tubule. Filtrate is being processed, so there's exchange happening between in the ascending and descending tubules, and by the time it gets back to the distal convoluted tubule, there is a initial amount of this. Macula densa is the sensitive cells on the distal convoluted tubule. It's a smaller size. They sense water and sodium left in the filtrate. Juxtaglomerular cells are sensitive cells tapping into the point of the filtrate. Kidneys needs feedback, so these sensitive cells are reading the DCT, reading it for pH, carbon dioxide, and filtrate levels. Next, going to the glomerulus. Blood is pushed into the afferent arterioles. The kidney assists with maintaining blood volume and blood pressure. The kidneys can sense blood pressure using the walls of the afferent arterioles, whose walls are sensitive to blood pressure. Reading the filtrate, feedback reception. Decreasing blood pressure means less water filtered out. So if there is decreasing pressure, then there's decreasing glomerular filtrate pressure, which affects the glomerular filtration rate. Decreasing filtering of water affects arterioles. The wall sense when pressure is low in water that is filtered. Water is taken out if the blood pressure is sensed to be low. Glomerular filtration rate is measured as a critical indicator of how well your kidneys are functioning. Affected not just by blood pressure, it's also affected by the back push of pulling fluid into the blood by osmotic pressure of pulling / keeping fluid in blood. You have to hope that you'll have enough hydrostatic pressure to keep pushing fluid out of the arterioles and into the capillary bed. On the venous side, there is a net pull inward because it is a loss of fluid out because of higher concentration in the blood. Fluids are not going out into an interstitial space. Fluids are going out into a capsule for some back pressure. Back pressure is produced by the capsule. Some important terms to understand would be hydrostatic pressure or blood pressure pushes fluids and ions into the capsule. Capsular pressure is the back push, so going back into the blood. Okay. Osmotic pull things back into the blood. The filtration pressure results from 3 pressures working back against each other. Net filtration pressure is measured in millimeters of mercury, shoot up with a net filtration pressure of fluid outward. So if there's a decrease in blood pressure, it means there's not efficient filtration. The filtration pressure will be in the wrong direction, so kidney disease, flowing in the wrong direction. How much fluid is filtered at the glomeruli? If we are not reclaiming the rest of the things, we were just looking at the fluid filtered at the glomeruli. We would produce 180 liters per day. Effective reabsorption process, so 2 liters of urine being reabsorbed per day. Importance of having the right pressure, having the osmotic part of the story right, how easy it might be to perturb kidney function. Kidney function is an indicator of what is going on in your heart and bloodstream, and tell ion levels in the blood. Preservations, things that are wrong, not filtering or filtering enough ions gives windows to blood pressure issues. Issues of passing ions back and forth need specific conditions to be perfect. The body has auto-regulation in each of the glomeruli. Auto-regulation by afferent and efferent arterioles. Filtration pressure needs to be right. The body has an auto-regulation mechanism. The ups and downs of blood pressure are accommodated by the arterioles. The afferent arteriole will sense the decrease in blood pressure. The walls will dilate, and efferent arterioles will constrict, holding blood in, allowing you to maintain normal pressure of afferent arterioles. Filtration site limiting the amount of blood and letting out more amount of blood out. So decreasing blood pressure, afferent arterioles will dilate and the efferent arterioles will constrict, allowing blood to maintain normal blood pressure. If you have high protein in your urine, high blood pressure sensed by the walls will cause the afferent arterioles to constrict a little bit by limiting blood going into glomerulus. High protein urine, that means increased pressure. Some of the proteins won't go through. The afferent and efferent arterioles are the first line of defense against fluctuating blood pressure. If blood pressure is too high, there would be times where some proteins are not being pushed out. High protein is a problem at the filtration site. Having a lot of protein is a problem at the filtration site. Okay, next figure. Oh, it's on the same figure. Proximal convoluted tubule. Proximal convoluted tubule has cells that are simple squamous. The thinnest membrane looks like outside wall of an alveolus for a quick passage of ions in small molecules in a short amount of time. The proximal convoluted tubule, another figure of that would be here. Proximal convoluted tubule. Cells have simple squamous epithelium. A lot of nuclei, brush border on microvilli, apical surfaces, lumens on the edge of cells, lumen with tubular fluid with cells, not simple columnar cells, simple cuboidal cells here. Most water can be reabsorbed in blood osmotically flowing through in blood by different. Everything that came out of the filtrate gets reabsorbed in the proximal convoluted tubule. Okay, relying on a few passive mechanisms, diffusion and osmosis. Water follows solutes diffusing back in by diffusion. Some active and passive solutes moving back into the blood by reabsorption into blood. So what has been accomplished? We have the same mix of solutes in the blood after reabsorption, because some of that remains in the kidney tubules. It's a mix of pre-urine in the tubules and critical things left in blood. You don't have to know the mechanisms too much. That's what the professor told us. There is active diffusion there is active diffusion and return of solutes back in the blood, reabsorption into the blood. After reabsorption, there is same mix of blood in the kidney. Ooh. In the kidney tubules, so the volume of tubules is lowering and the concentration is mixed. So this was a bit of a struggle filming this video, but it's early in the morning. Got a quiz soon, so you gotta do what you gotta do to study. Kidneys, reabsorption, secretion, big stuff. See you guys in the next one.